Question number 4. So the radioactive nuclide beryllium undergoes a beta minus decay to form a stable boron nuclide. Okay, and now identify the missing information for this decay. Now what is missing here? So here it is boron. So this is minus 1. Put minus 1 here, E0 here. This is your anti-neutrino. So what will happen here? So if this is 10, this will also be 10. 10 plus 0. So mass number is balanced. Now here you look at this is 5 minus 1 should be 4. So it will be 4. Okay. So these two are important. Get full mark load. Okay, next. The initial number of nuclei in a pure sample of beryllium is 10 is N0. The graph shows how the number of remaining beryllium nuclei in the year simple years with time. Okay. So varies with time. Sample varies with time. Sorry. Okay. So fine. On the graph, sketch how the number of boron nuclei in the sample varies with time. What is being shown over here is the decay of beryllium nucleus with time is being shown over here. What is being asked is that how does the growth of boron nuclei happens? Okay, how do we do? See, if the initial number of nuclei here is N0, after one half-life, the beryllium nuclei becomes 0.5 N0. So therefore, let me consider this point. So this point, if I draw a line here, this will be your half-life. Okay. So which means when this decreases to half of this, what has happened to that half with the decay? This has become decayed from beryllium to boron. Let us say, for example, if beryllium, if there are 100 atoms initially, 100 nuclei initially, number of boron nuclei was 0 initially. Okay. Then after this half-life, if this became 50, this would also become 50 because this 50 has got converted into this 50 here, right? So therefore, now what I need to do is that the growth curve should be 50. So one of the coordinate is known to me. Now, second coordinate. See, at the end of somewhere over here, at this point, what is the total number of nuclei? This seems to be around 0.2 times N0. 0.2 times 0 N0. Okay, which means what? 0.n times N0 has already got converted into boron. Which means this coordinate, what is this coordinate? The y coordinate here, and there should be one more y coordinate which should be seen over here. Sum of these two should amount to N0. That's what is the question over here, right? So number of nuclei here plus number of nuclei here should be equal to N0. So if I know this at every point, then definitely I get a correct answer, right? So therefore, now I should draw the curve in such a way that this condition should be satisfied. What is the condition? Number of boron nuclei, number of beryllium nuclei plus number of boron nuclei should be equal to N0. Okay. So every grid I will not be able to map. So what I will do is I will already choose on one point here, one point here. If you need one more point also you can choose. Okay. Which point shall we choose? For example, this point 25 N0 at this point. At this point. What is this number? At this point, this should be 0.25 N0. The boron number should be 0.75 N0. Where is 0.75 N0? It is somewhere over here. Okay. I want to draw a smooth curve, right? Okay, so I will take this one. If you want, I will take one more here also. Where is it? 0.75 N0 is here at this point. So therefore 0.25 N0, where is 0.25 N0? It's here at this point. So at the same timeline, at this point, you have got here. I have got 1, 2, 3, 4 coordinates I got. I can easily draw a smooth curve. That's it. Right? So this will give you a problem. So without any mistake, if you want to do it, this is what. See, whenever you are drawing any curve in physics, the first thing is that look for the data. Where is the data available? How do I get the data? What assumptions I am making? So this should be clear to you. If you know this, definitely solving any physics problem is not at all difficult. Quite easy. Okay, next, let's move on to this. On the graph, sketch how the number of boron nuclei in the sample varies with time. Okay, we have done this part. No problem. After 4.3 into 10 power 6 years, number of boron nuclei, produced boron nuclei by number of remaining beryllium nuclei is equal to 7. Show that the half-life of beryllium is 1.4 into 10 power 6. Wow. So how do I do this? So it says number of boron nuclei. I'll write down. Number of boron nuclei divided by number of beryllium nuclei. Beryllium nuclei is equal to 7, which means what? Number of boron nuclei equal to 7 times number of beryllium nuclei. First condition. Secondly, we know that number of boron plus number of beryllium is equal to N0. This also we know. Now what I will do is I will take this condition, substitute here. So what do I get? 7 times N beryllium plus N beryllium is equal to N0, or N beryllium is equal to N0 divided by 7 plus 1 is 8. I get this value here, which means what? At that instant when you say something like this, N beryllium was N0 by 8. That means after this much amount of years, number of beryllium nuclei which was in hand with me was only seen to be 1/8 of the total number. Now, what does it mean? Which means that initially I would have had N0 atoms. This would have become N0 by 2. This will once again become N0 by 4. This will once again become N0 by 8. Okay. In what time? One half-life, second half-life, third half-life. Of course, there is a formula for it. I'm not using the formula. Okay, I'm just going from the scratch. So even if you forget the formula, you should be know how to do it. Okay, so therefore 3 half-lives is equal to this much, right? So that's what it says. After this much years, so this much amount of beryllium was remaining, right? So this should now be equal to 4.3 into 10 to the power of 6 years. One half-life is equal to 4.3 divided by 3 multiplied by 10 power 6. So let us do this math over here. And do 4.3 divided by 3. Roughly it comes out to be 1.43. So 1.43 into 10 power 6 years, which is nothing but, if I take two significant figures only, this one becomes 1.4 into 10 power 6 years, right? As needed over here. Okay, now let us move on to the next question. Beryllium-10 is used to investigate ice samples from Antarctica. Okay, a sample of ice initially contains 7.6 into 10 power 11 atoms of beryllium. 7.6 multiplied by 10 to the power of 11 beryllium atoms. What is this value? It's your N0 over here. Okay, state the number of remaining beryllium nuclei in the nucleus in the sample after 2.8 into 10 power 6 years after this time. Now let us take the half-life. What is the half-life here? 1.4. Let us write down. So half-life is equal to 1.4 into 10 power 6 years. Now what is this now? 2.8 is twice of this, which means after one half-life, this would have become 3.8 into 10 to the power of 11. After one more half-life, that means after 2.8 into 10 to the power of 6 years, this would have become 1.9 into 10 to the power of 11 years. 11 atoms. What has been asked? State the number of remaining beryllium atoms. We already got the answer. Okay, so thus you got the answer as 1.9 into 10 to the power of 11 atoms. Okay, all the problems are quite easier. Only thing is you should know how to use the proper formula. Next. Okay, an ice sample is moved to a laboratory for analysis. The temperature of the sample is minus 20 degrees centigrade. Okay, state what is meant by thermal radiation. Now when you say state over here, which is for 1 mark, you need to just explain about what is this about. You know, you're not going to put this value anywhere over here. It is thermal radiation. Thermal, what is thermal? Hot, right? Something which is hot, which is getting radiated. So what is I mean by hot, which means IR radiation. Okay. IR radiation. But is this the answer? No, it's not the answer. You should mention energy radiated by means of heat, or IR radiation, or in general electromagnetic waves, okay, is known as thermal radiation. This is what you need to write. Don't just mention it is nothing but IR radiation or heat and so on. Okay, then next, discuss how the frequency of the radiation emitted by a black body can be used to estimate the temperature of the body. What is he asking? How does you need to discuss the frequency? Depends on temperature. How is a frequency a function of temperature? Now when you have this, so what should come to your mind? You should say the temperature, when you increase the temperature, the wavelength of the radiation is seen to be decreasing. Where do you get this from? This is your Wien's displacement law. Why am I using here? Because of radiation. In radiation, there are only two laws. First one is Wien's displacement law. Second one is the Stefan-Boltzmann law. Okay, so we are using this one here. So therefore, temperature increases, wavelength decreases. And then since frequency f is equal to c by lambda, which means as lambda increases, or maybe since we have discussed about lambda decreasing, frequency will increase, or frequency is directly proportional to temperature. That's what you can say. Thus, you can use the temperature. Okay, so you can use the frequency of the radiation. You can determine the frequency of the radiation. Find out the temperature of the hot object. See, because if I ask you what is the temperature of the sun, you cannot take a thermometer and go to the sun and measure it, right? Or you cannot send a rocket or maybe a satellite to go, space shuttle to go to the sun and measure it. So what you do is you find out what is the frequency of radiation it emits, and then on an average you say these are the composition or this is the temperature of the object. Okay, now let us move on to the next question. Calculate the peak wavelength and intensity of radiation emitted by the ice sample. How do you do it? So we know from Wien's displacement, lambda into T is equal to B. This is a constant. So this is nearly 2.9 into 10 to the power of 11. 2.9 into 10 to the power 11. So give me a moment. Let me find out the exact value of the constant. I have written somewhere. 10 power minus 10 power minus 10 power minus. Okay. So what is that he is asking? Peak wavelength. This is your peak wavelength. Lambda peak is equal to 2.9 into 10 to the power of minus 3 divided by temperature. Now what's the value of temperature over here? See, always remember whenever you are talking about thermal physics, temperature should be in Kelvin only, it should not be in degrees Celsius. Now that is the reason why he has given you in terms of degrees Celsius. So what you should do? You should substitute this value in terms of Kelvin. So this should be 2.9 into 10 power minus 3 divided by 273 minus 20, because minus 20 is the temperature of the ice that is saying. So thus you can write 2.9 into 10 power minus divided by 253. When I do this, let us see what we get here. 2.9 it be 0.011 into 10 power minus 3. So how many significant two significant figures are? It be 1.1 into 10 to the power of 12 10 power minus 5 unit meters. Okay. Meters over here. So 1.1 into 10 power minus 5 meters is the intensity of the radiation emitted by the ice. Then derive the units of intensity in terms of fundamental SI units. Intensity. What is intensity? He is only asking you to get the units, nothing else. Okay. So no derivation over here. Intensity is nothing but power per unit area. What is power? Power is nothing but force into velocity divided by area. Or you can also say work done divided by time. Anything is fine. I usually use this one. If you want, I can do that one also. So then what is force? Force, unit of force is nothing but Newton. But if it is in terms of fundamental unit, I'll write it as mass into acceleration multiplied by V divided by area. Okay. So what is mass? kg, acceleration meter per second square, velocity meter per second divided by area meter square. What will happen? Meter square, this meter goes in. So what am I left out with? I am left out with kg per second cube, which should be kg s to the power of minus. So this should be our answer. Okay, though this is a long question, it's worthwhile. It connects two different units. Thus, come to an end to this particular question. Let us see tomorrow with a new question. Thank you.